Good morning. Myself souptik patra from Coachbihar Government Engineering College under Computer Science and Engineering Department. Today is our topic logic gates, which belongs to analog and digital electronics subject. First of all, we need to understand what is logic gate. A logic gate is a fundamental building block of digital circuits and electronic devices designed to perform basic logical operations based on input signals and produce the output signal according to predefined rules of logic. These gates are the foundation of all digital computing systems and are essential for processing and manipulating binary data. Obviously, there is large number of logic gates. From them, we are talking about only seven, which are important. From them, NOT gate, AND gate, OR gate, NAND gate, NOR gate, XOR gate, and lastly XNOR gate. First, discuss with NOT gate. The purpose of the NOT gate is to complement or invert the input signal, producing the opposite logical state at the output. Secondly, NOT gate is also called inverter or negation logic. NOT gate works as a buffer when even number of NOT gate used in a series in a circuit. NOT gate are used as a basic memory element when propagated through feedback wire. NOT gate sometimes used in circuit for time dilation or give the time dilation. NOT gate takes only one input and gives only one output. Here is the diagram of NOT gate, and the truth table explains that whenever you give the inputs, the output is just complement of the input. For example, if you give 0, the output will be 1. If you give 1 as input, the output is 0. Logical expression is defined as z equal to a complement, where z is the output. Next, our gate is OR gate. An OR gate in digital electronics and logic circuits is a fundamental logic gate that performs a logical union operation. OR gate is control zero enabled, also called ECL enabled, while ECL stands for emitter coupled logic, and OR gate is control 1 disabled, also called TTL disabled, where TTL stands for transistor transistor logic. The logic follows commutative law as well as associative law. Here you can see the mathematical expressions of them. Here the diagram of OR gate, and the logical expression of OR gate is y is equal to a plus b. And the truth table of OR gate explains that the output will only 1 when there was at least 1 times high output is present. For 0, 0 and 0, second possible combination is 0, 1, 1, 1, 0, 1 and 1, 1, 1. Our third gate is AND gate. The purpose of the AND gate is to perform a digital intersection operation on its inputs and produce an output based on the result of the operation. It is control 0 disabled, also called ECL disabled. AND gate is control 1 enabled, also called TTL enabled. The logic follows commutative law as well as associative law. The mathematical expression describes that. Here you can see the diagram of AND gate, and the mathematical expression or logical expression explains y is equal to a dot b, where y is the output. And the truth table defines that if there was at least 1 time 0 present in the input bit, the output will 0 anytime. Our fifth gate, NAND gate. A NAND gate is short for not AND gate. It is fundamental logic gate in digital electronics and logic circuits. The NAND gate performs a logical NAND operation, which is the complement of the AND operation. We will get NAND gate by complementing both input of an OR gate, which eventually called as bubbled OR is NAND. Then NAND gate have a unique property in that they are universal logics, which means that any other logic functions can be constructed using these NAND gates. They are widely used in complex logic designs, memory units, microprocessors, and other digital applications. Our NAND gate is control 0 disabled, also called ECL disabled, and control 1 enabled, also called TTL enabled. It follows commutative law but doesn't follow associative law. Here we can see the circuit diagram of NAND gate, and its mathematical expression explains that y is equal to a dot b whole complement, where y is the obviously the output. Here we can see the truth table, which explains that the output of NAND gate is just the complement of AND gate. Next, next logic gate is NOT gate. A NOT gate in digital electronics and logic circuits is a fundamental logic gate that performs a logical NOR, or you can say NOT OR operation. NOT gate performs a logical OR operation on its input and then negates the result. We also get NOR gate by complementing both input of AND gate, which eventually called as bubbled AND is NOR gate. NOR gate is also an universal gate. It is control 0 enabled, also called ECL enabled, and our NOT gate is control 1 enabled disabled, control 1 disabled, also called TTL disabled. It follows commutative law but doesn't follow associative law. NOR gates are widely used in digital circuits and are important building blocks for various applications. While making NOR gate from DCTL, a current hogging problem occurs. From them, we can conclude that NOR gate in some scenarios are not considered as a universal logic gate, just like NAND gate. Here is the diagram of NOR gate, and the mathematical expression is y is equal to a plus b whole complement. And the truth table can clearly see that the outputs of NOR gate is just the opposite of OR gate, and it should be obviously, as the name suggests. Our next gate is XOR gate. An XOR gate, also called as exclusive OR gate, is a digital logic gate that performs the exclusive disjunction operations. The XOR gate is widely used in digital circuits, computer arithmetic, and various other applications where exclusive disjunction is required. It is also fundamental building block for more complex logic functions and circuits like adder and subtractors. XOR gate is also called as odd parity detector due to its output will only come high when there's odd number of 1 is present as input bits, and our XOR gate is also called as even parity detector. Even parity generator. ECL enabled as buffer in XOR gate and TTL enabled as inverter in XOR gate. Our XOR gate follows commutative as well as associative law. Here we can see the mathematical expression and the diagram of XOR gate, where mathematical expression is defined as y is equal to a XOR b, and the breakdown of a XOR b as a b bar plus a bar b. The truth table. In XOR gate, the truth table is more interesting and is defined as we can see if there is odd number of 1 is present in input bits, the output will get 1, and thus XOR gate is called odd parity detector. Our last gate is XNOR gate. And XNOR gate, also called as exclusive NOR gate, is a digital logic gate that performs the exclusive NOR operation. It is a complement of XOR gate. XNOR gate are often used in digital circuits to compare two binary bits and check for equivalence. The XNOR gate is widely used in digital circuit and computer arithmetic. Commutative law follows, but associative law doesn't follow on XOR gate for even number of inputs. Or we can generally say that XNOR gate doesn't even exist without even number of inputs. After that, our XNOR gate can be talked as odd parity generator and even parity detector. That's mean the output will only gives high whenever this even number of 1 is present as input. Our XNOR gate is ECL enabled as inverter and TTL enabled as a buffer. Here you can see the circuit diagram of XNOR gate, and the mathematical expression defines y is equal to a XNOR b, and the breakdown of this formula is a bar b bar plus ab. Here you can see the truth table. Here you can clearly define that the output bits is just the complement or opposite of XOR gate. Or even we can clarify that the outputs will only come high when there is even number of 1 is present as input. Thank you. That's the end.